about a pivot point at its middle. So I want you to imagine just some oddly shaped object. Doesn't have to be regular or anything like that, but some object that's going to be spun about some point, not necessarily its center of mass, just some point. Some of the definitions you need to understand are relatively straightforward. This object has angular momentum. We use a capital L as a symbol for angular momentum. It is a vector quantity, so I put the bar on it. And it is a product of the moment of inertia times the angular speed. It has a direct analogy to linear momentum. Remember, linear momentum, lowercase p, bar on top of it, and that's equal to mv, bar on top. So clearly a direct relationship here. Now, we talked about energy last week and the week before. Something that's spinning has rotational kinetic energy. And in our prior discussions, we know that the translational and kinetic energy are still compatible things. So an object that's spinning and moving or changing location has two forms of energy, and they will sum to contribute to the total energy of the system. Momentum is different. These two values, linear momentum and angular momentum, aren't the same. This item could be drifting through space with a velocity v and a mass m, and it would have a linear momentum that is distinct from its angular momentum. Although they are related, perhaps, we don't say their total momentum by adding these up. It doesn't work that way. Angular momentum is a different unit than linear momentum. Linear momentum is kilograms meters per second. We don't have a special name for that. Angular momentum, if you look at the units here, is kilograms meters squared per second. So we're talking about something that doesn't even have the same units. So there's no way to say what is the total momentum of the system. We don't do that. We can talk about the total angular momentum of a system as distinct from the total linear momentum of the system. And like I said, they can be related. You can have something that causes a torque and a force at the same time. You could walk up here to this object as it's moving and push, say, right there with some force. And it would probably change the rotational speed and change the linear speed. But how it affects each isn't the same. So when we deal with angular momentum, we tend to deal with it by itself, talking about the angular momentum properties. And we deal with linear momentum, we tend to deal with it by itself. Now, I know it's not a hard and fast rule. We just need to take it case by case. Please remember, there's still things like impulse. Impulse, by definition, still stays the same. It is the change in momentum. And it occurs because of an unbalanced force acting over some time interval. We talked about that yesterday. Now, could you please study what I'm about to tell you? Because we talked about it last year, but it didn't sink in. This force has nothing to do with the direction of the momentum. I mean, look at this object. It has a momentum in this direction. The applied force is in that direction. It's going to cause a change in momentum. So when you look at this, please be aware that delta P is in a direction of the change of momentum, not in the direction of the momentum. It's in the direction of the change in momentum, not in the direction of the momentum. Yeah?
Is that the same for rotational too, because it has torque in it?
It's going to be very similar. That's what I'm about to do, to give us the analogy there. So there is angular impulse. And as you probably expect, it's the change in angular momentum. Now, generally, for our spinning objects, our change in angular momentum is going to be about spinning it up faster or slower. So it tends to be more one-dimensional. But I want to emphasize, it doesn't have to be. The torque can be in any direction. So the angular impulse is in the direction of the unbalanced torque. Now, none of these are earth-shattering ideas. If you want to change something's momentum, it requires an impulse. And an impulse occurs due to a force. Now, all that being said, please in your notes, somewhere, remind yourself that in a system where momentum is conserved, the net impulse has to be zero. In a system where momentum is conserved, the net impulse has to be zero. So anything that increases momentum will have something in the system that decreases their momentum. It's the only way for the net impulse to be zero. So if you have 1,000 objects that are all considered your system, if one of those objects starts to go faster, then somewhere in the universe, another object went slower. That's what defines it as a system. So a bullet strikes a block. The block goes faster. It had a positive impulse. The bullet's going slower, negative impulse. That's going to be true for angular momentum too. Now, I want to start out with relatively straightforward questions. Ones that don't require a whole lot of deep calculation, but can be straightforward enough for us to observe. And I tend to stay with merry-go-round questions because they're relatively easy. They tend to involve simple things. So I think we can kind of visualize merry-go-round questions okay? So I want to start with a simple merry-go-round question where I have perhaps 2 children on a merry-go-round. And let's establish that the merry-go-round has a mass of 300 kilograms and a radius of about 3 meters. And let's also establish that the kids are 40 kilograms each. Now, this first angular momentum question we're going to talk about is not at the level of AP. It's just basic. It's to give us some experience looking at angular momentum. So we're going to walk through several different cases of this question. So I kind of want to give you some experiences seeing how torque creates angular momentum, and then from there, how changes in moment of inertia affect the angular speed. That's this example question. So as an example goes, and I'm going to try and do the examples a little differently here because it hasn't always sunk in. I'm going to give us the long view and then the piece by piece. Okay? So the long view is that I want you to see how a problem can transition from one in which there's an external force on the system to one where the system is experiencing no external forces. and some things to look at in dealing with that. For example, a third child stands off the ride, right here. They apply a 50 Newton force for 10 seconds. So they push right here with a 50 Newton force for 10 seconds. What impulse did they impart to the ride? So our first question, and look, so again, the kid standing on the ground is fixed in place. Because of that, there are forces acting on the kid from the ground to hold him there. Not true for the two kids that are on the merry-go-round. They are part of the merry-go-round system. So the torque applied to the merry-go-round affects everything on the merry-go-round. So in this question, we're dealing with an external, unbalanced torque that's acting for some period of time that's going to cause a change in angular momentum. Now, we could do this problem instead as a motion problem where we find the acceleration and use that to get the velocity, but we're not going to. We're going to do this as an impulse question. But you could do it the other way. You could say net torque equals I alpha, and then use alpha in a motion equation. That would work out just fine. I'm choosing not to do it that way to demonstrate there are alternatives, but you could. It's the same thing. Any unbalanced torque has to cause an acceleration. Any unbalanced torque. That's what this is. We can't get away from the fact that there's a torque applied, and which means that we need to consider the three things related to torque before we can go on. That doesn't change no matter what the circumstance is. And I think we can arguably agree that we have all the information to calculate this torque. We know the torque is being applied 3 meters from the edge of the ride, and that it's a 50 Newton force that's causing this torque. And due to the fact that it's on something round and the lack of any other information, we can probably assume that the angle that it's applied is perpendicular to the torque arm. Thank you. I'll take care of it. Justin, the pass for you to go to the counselor's office, but you're not going to be done to the end of the class period, okay? So, it's just for bright future stuff, so it's no big. So in this case, the torque applied by the kid is going to be 150 meter newtons. Questions about that? Relatively straightforward? So I don't think it's a lot here, but I am trying to go diplomatically slow to indicate that we can now take this and calculate the net impulse. I don't have any symbol for impulse. I'm not going to use it that way, and we won't use impulse very much. We tend to use it to figure out something that has happened or to figure out what has caused a change. So calculating the impulse is not very interesting, but I will state that when you calculate impulse, you are going to get something that is in terms of momentum. The units should be momentum. So in this case, the impulse would be 150 meter newtons times 10 seconds, giving me 1,500. And here's where we should take a close look at the units. Meters times Newton, which is kilogram meter per second squared, times seconds. Just taking a look at the units, because units are one of those things that we tend to kind of forget about till the end, but I hope you notice that one of the seconds cancels out here, leaving me with seconds in the denominator, and I have meters times meters. So that's going to give me 1,500 kilograms meters squared per second. And that's the unit for angular momentum. It's kind of what we expect. Now, if our question was about finding out the angular momentum of our system, we have probably found it out. I think we can all agree that it's likely the merry-go-round wasn't moving when the kids got on it, and this kid was nice enough to get it up to speed. We don't know how fast it's going, but we know what the angular momentum of the system is. That's what we've calculated. Any question about that? Relatively straightforward? All right, so assuming the third kid does not get on the ride, you calculate what the angular speed is, because that's a problem we've done before. And I'll give you a few moments to do so before one of you will help me. What am I going to do with that information? That's not really where I was going with it. We have the angular momentum. So how do I calculate angular momentum? Like what do you do to calculate angular momentum? It's in your notes, like one page back. All right, so angular momentum is I times omega. Of those three letters, which one do you have right now without doing any other calculation from what we did earlier in this problem? No. One down, two to go. What? Nope. That's why I need you to be more involved. Got it, Chris? So we have 1,500 kilograms meters squared per second as the angular momentum. We're going to set that equal to I omega. So I would have expected that you guys were busy calculating I, because that's what we didn't have. Because you're going to need that to figure out omega. So Jackson, how do you calculate I? What must I do?
So for the disk, it would be 1/2 mr squared, right?
Good so far.
Since there's 2 kids on there, it'd be 2 point masses.
Okay.
So 2 mr squared.
Did you use 3 for the radius of the kids?
Yes.
Yeah, or for the distance away from the pivot point, I mean? All right, so I would expect you guys to have done that. Any problem with that? So Jackson, did you get a number here?
Yeah, the total rotational inertia, we got like 2,070.
2,070, wow. And that's kilograms meters squared is the unit. And we have 1,500 kilograms meters squared per second as the angular momentum. So all that's left for us to do now is to find omega, which is going to be in no units per second. So what's our actual unit for our answer? Sure. So omega will be radians per second. It's quotient, and it's going to be something that's about 3/4, but probably a little more, right? So what, 0.7 what? 7.2? All right. Radians per second. I don't know how fast that is. You know, probably could figure it out, but it doesn't seem like it's very fast. Now, there's a couple different places we can go from here, but this is old news, right? It's not really a new way to do this problem, just a different way to do this problem. But we've done this problem before, so I don't feel like we've gone very far here. The next thing, though, would be new. What if the kid wants to join his friends on the ride and just jumps on it right on the edge? Now, before doing any work, what's going to happen to the speed of the ride if he just jumps on it? Okay, so we have a general idea for physics that if he jumps on it, the ride's going to slow down. Now, it's because of all sorts of things, friction mostly. When he jumps on it, friction is going to speed him up but slow the ride down. There's going to be an unbalanced torque on the kid and an unbalanced torque on the ride. So the kid's going to experience an impulse and the ride's going to experience an impulse. However, is there an external force on the system? Something that acts the same on both the kid and the merry-go-round? Now you might think gravity, but gravity acts straight down into the board on this problem. So although it's affecting them all, there's also an upward normal force that balances it. So in this case, gravity isn't an external torque. It doesn't act to rotate the system. So I believe we can use conservation of momentum in order to figure out how fast the ride is going after the kid jumps on it. So that's what I'd like you to do. I'd like you to treat this like a conservation of momentum problem. To do so, we start by recognizing that the angular momentum before it's got to equal the angular momentum after. These are collision questions. So the things you should look for is that there was nothing else involved in pushing on the kid or the ride but the kid and the ride. And once the kid stepped off the ground, there was nothing holding him in place. He removed the external force that was acting on the system to keep him firmly on the ground. Those are kind of banner pieces of information to help you realize this is a conservation of momentum question. And also, it's kind of it looks like a collision, doesn't it? Like when we talked about collisions before, when an object struck something else and they stuck together, that's what's happening here. The merry-go-round was moving. It struck the kid, whom afterward is now moving with the merry-go-round. It's all the hallmarks of a perfectly inelastic collision. Collision questions should help you trigger or think of conservation of momentum. Now, this part is relatively easy. We know the angular momentum before already. It's still 1500. That hasn't changed. So when you can, try and use information that's already been used in the problem. Don't recalculate it to find out it's 1500. On the other hand, the moment of inertia has changed. Because although the kid adds his moment of inertia to the problem, there was already an established moment of inertia of 2070. All we need to do is add one more kid, assuming he's the same mass. We add one more point mass to the edge of the ride. Now remember, we have an expectation here that the ride's going to slow down. You do this and your ride speeds up. You did it wrong. Pay attention to that. Our original speed was 0.72. What's our new speed? I know somebody's already done it. Yes, sir.
0.62.
How many of you got 0.62? Anybody else verify it? Great. That agrees with our expected idea that the ride is going to slow down. So what you just saw here is an example of a type of collision, a rotational motion collision. And that's kind of what it will look like. This is a very common question in this class. And now at this moment, the kid's on the ride. So this next piece, I think you guys can do as well. What if all of the kids immediately walked to the very center of the ride? Now this one you might not know what to expect as an answer. But if my demonstration holds, what do you think is going to happen to the ride? It's going to speed up. Is the angular momentum of the ride going to change? Now, this part's something that students get wrong on tests a lot. The ride's going to speed up, but the angular momentum of the system isn't going to change. So what's the angular momentum of the system after the kids walk to the center? Say it with confidence. 1,500, yeah. The angular momentum of the system is now fixed. There's no external forces acting on the system. All that's happened is the three kids have moved to the center. Let's put something somewhat real. Let's say that they are 0.2 meters away from the center, each of them. So they all walk to the center and huddle in the middle. What will be the new speed of the ride? Now, can I assume most of you are hurriedly trying to find the new moment of inertia of our system? And of course, you've calculated part of it before, so I hope that you are recognizing that should you be keeping good notes, you might have these things already written down. In an FRQ, there's a reason to kind of write pieces down. But at this point, there are three kids, all of them of mass 40, all 0.2 meters away. This drastically reduces the moment of inertia of the system. Did anybody get it already? No, I just want the moment of inertia because not everybody got that far. 1354.8. So you should definitely see a distinct increase in the angular speed. And you said what? 1.1 radians per second.